Assalamualaikum and good day to all students. For this video, we are going to cover for tutorial of chapter 6, whereby tutorial chapter 6, if I'm not mistaken, we have two tutorials. One is tutorial 6.1, whereby this one is basically meant for the conduction, okay, heat transfer by conduction. Okay, and then the second one, tutorial chapter 6 for number 2, that one is meant for heat transfer by convection, whereby it involves with the liquid flow. Alright, so now let's move on for the first tutorial of chapter 6. Okay, so please take a look for your question. For tutorial 6 number 1, question number 1, a cork slab whereby it has 24.6 millimeter thickness has one face at 322 Kelvin and the other face is at 281.7 Kelvin. If the mean thermal conductivity of the cork at this temperature range is 0.048 watt per meter Kelvin, calculate the rate of heat transfer per 1 square meter wall. Alright, so for this particular question 1 is very simple, whereby you just plug in the equation Q equals to K over X A delta T, and the answer should be 78.63 watt. Alright, now let's move on to question number 2. For question number 2, you have question 2A as well as question 2B. Alright, so for question 2A, a coal store has a wall comprising of 11 cm of brick on the outside. Okay, so this is the diagram that I have drawn for you, so you can refer to this particular diagram. So the first material is made from brick and the thickness is 11 centimeter. Alright, on the outside, so this part is at the outside. Alright, and then followed by 7.5 centimeter of concrete. Okay, the thickness is 7.5 centimeter. Followed by 10 centimeter of cork material. Okay, so the mean surface within the store is maintained. Alright, so this one is the inside of the store. So the mean temperature is maintained at negative 18 degrees Celsius, and the mean temperature of the outside of the surface wall is at 18 degrees Celsius. When we talk about the surface, okay, so this one is the this particular part is the area of the store. So normally when we measure the temperature, we will measure on the surface of the wall over here. So at the outside also we are measuring at the surface of the wall. Okay, not on the other part. Normally it will be on the surface of the wall. Okay, so for question number 2A, calculate the rate of heat transfer. Okay, so you need to calculate for the value of Q. Calculate the rate of heat transfer through the wall. Thermal conductivities for the materials are given as follows in your tutorial. So you can see that the arrow of the temperature is moving from your left hand side towards your right hand side. Okay, why is that? Because it's according to the law of energy, whereby the heat will be transferred from higher temperature to lower temperature. So T1 is having higher temperature compared to T4. So the movement of the heat being transferred is from the hotter region to colder region. Alright, so in between this particular wall material, we have brick, we have concrete, and then we have cork. So on the surface of each of these particular two material, we have another T2, another temperature surface. Okay, surface temperature, and then in between concrete and cork also we have another surface temperature. This one is T3. Alright, so the first one, what you need to do is you need to solve for the value of U, overall heat transfer coefficient. So this one, you just use the equation of 1 over U equals to X1 over K1. This particular value, number 1, number 2, number 3, it's really up to you whether you want to put number 1 as brick, number 2 as concrete, number 3 as cork, or the other part, or vice versa. So totally it's up to you, but you must make sure that the material number 1 must be consistent for material for the value of K1. Okay, for material number 1, it should be together with the value of K1. Okay, you should not mix up these particular values. Alright, so just use the equation of 1 over U equals to x1 over k1 plus x2 over k2 plus x3 over k3 because we have 3 materials. Okay, we have brick, concrete as well as caulk. Alright, so calculate the value of U, then you will get the value of 0.38 joule per meter square second degree Celsius. Alright, and then calculate the delta T. Delta T simply minus temperature from T1 minus by T4. Okay, so the value for delta T is 36 degrees Celsius and it is given in your problem statement whereby the area of the this particular surface is 1 meter square. Okay, so when we talk about the surface area, so each material they are having the same surface area. Alright, and then so we have all the values, so just plug in equation of Q equals to UA delta T, then the equation should give you an answer as 13.7 joule per second. Alright, now let's move on to question number 2B. Interfacial temperature between caulk and concrete. Okay, so for question number 2B, you are going to determine for the temperature of T3. Okay, this particular surface temperature in between concrete as well as caulk. So from Fourier's law, so we have 3 material. This one is material 1, this one is material number 2, this one is material number 3. Okay, so now what is your main reference will be material number 3. Okay, why material number 3? Because for the fourth part, okay, inside of the store, this one I label as number 4. Because this number 4, we have a temperature. Okay, we have a temperature value on the surface of this particular wall in the inside of the store, whereby if let's say you take your temperature difference between T2 and T3, that this particular T2 and T3 there is a no value, no single value for the temperature. Okay, whereby for T3 and T4 we have at least one temperature value for T4. Okay, at least we have one reference of temperature. So in order for you to solve this problem, so you need to find the delta T between T3 and T4. So this particular delta T3 basically is T3 minus by T4. But you just stick this particular label as this delta T3 because I do not want you to confuse where you are going to put in the value T4 at negative 18 degrees Celsius. This particular value of T4, this one will be later. This one will be over here on the second step of the calculation. Alright, so what's happening here, you just use the equation of Q equals to K over X, A delta 3, but this one is meant for the material number 3, this one is meant for the caulk. Alright, so this T3 is meant for the caulk. And then this particular Q, okay, remember that the value of Q is equivalent at all surfaces. Okay, so Q1 is equals to Q2 is equals to Q3. So at any part of this particular material, you are going to have the same value of Q. So that's why just now we have calculated for question 2A, whereby the value for Q has been determined, 13.7 joule per second. So just use again this particular value over here, alright, 13.7. Okay, and then this particular K3 over X3, this one has been given to you, so just plug in the values. Alright, and then the area for A3 is 1 meter square, alright, because the surface area at any material is the same thing, okay, this particular area. Alright, the only unknown that we want to calculate will be delta 3. So the value for delta 3 after you have calculated, you should get the value of 32 degrees Celsius. So this one will be the temperature difference. Okay, temperature difference is this one between the caulk surface and the concrete. Okay, it will be basically in between T2 minus T3 and the temperature of caulk surface inside the cold store. Okay, caulk surface inside the cold store, this particular surface. Okay, hence the temperature between caulk and concrete, so T2 minus by T3, but we want to make sure, sorry, not T2, T3 minus by T2, but we want to have the value for T3, this particular T3, because this particular T3 is the temperature between cork and concrete, okay, this particular surface, T3. So what's happening here is that 32 degrees Celsius, the delta T that we have calculated just now, is equivalent to T3 minus by T4. Okay, since we have known that the value of T4 is negative 18 degrees Celsius, so just just add in the values and then calculate, and you should be able to get the value of T3 is at 14 degrees Celsius, meaning the temperature between the concrete and cork is 14 degrees Celsius. So the same thing goes if, let's say, the question asks you to calculate for the value of the temperature surface between brick and concrete over here. Okay, brick and concrete over here, the same thing goes, but you are going to take your reference temperature from T1, 18 degrees Celsius. Okay, do not take the value of T3. For example, this value of T3 is unknown, and T2 is unknown as well. So you need to calculate the value of the temperature surface between brick and concrete. So the same thing goes, you will going to use the reference temperature of T1. Okay, so please practice for this particular problem statement. Alright, now let's move on to another question. Okay, for question number 3, sugar solution is being heated to 83 degrees Celsius in a jacketed pan made from stainless steel, 1.6 millimeter thickness. Okay, so the stainless steel, it has the thickness of 1.6 millimeter. Heat is being supplied by condensing steam at 200 kilopascal gauge in the jacket. Calculate the rate of heat transfer if the surface heat transfer coefficient for condensing steam and sugar solution are 12,000 joule per meter square second degree Celsius and 3,000 joule per meter second degree Celsius respectively. Okay, meaning that the heat transfer coefficient for the condensing steam is 12,000, whereby for the heat transfer coefficient of sugar solution is 3,000. Okay, thermal conductivity for stainless steel is 21 joule per meter second degree Celsius, whereby the surface area of the pan is 1.4 meter square. Okay, so it gives you the hint whereby you need to use a steam table in order to determine the temperature for condensing steam. So please take a look for your steam table, whereby you need to use the, if I'm not mistaken, for the first attachment. Okay, look for the pressure, the column of the pressure. So at the column of the pressure at 200 kilopascal, so what will be the temperature of the steam? So when you look at the steam table, then you will see that you need to do some interpolation. Okay, for this particular question, you need to do some simple interpolation. Then you will get the value of temperature is 120.22 degrees Celsius. Okay, so this particular temperature is required in order for you to calculate for delta T. Okay, so delta T, this one, can you see that we are using condensing steam temperature? So this is the value that you have found just now, and it needs to be used for this particular calculation of delta T. Alright, so condensing steam temperature is 120.22 minus by 83. This one has been given for the sugar solution, temperature of sugar solution. Then the answer is 37.22 degrees Celsius. Alright, now we move on for the calculation of the overall heat transfer coefficient. So since this material, we have steam, okay, we have steam, and then we have sugar, followed by the stainless steel. So you need to use the surface heat transfer coefficient, whereby the equation that you need to use is 1 over U equal to 1 per HS1. Do you remember that you need to calculate for 1 over U equals to 1 over HS1 plus X over K. It depends on how many materials that you have. And then followed by 1 over HS2. Okay, this one is for one material, and this one is for the other material. Alright, whichever that you want to number as number 1 or number 2 is totally up to you. Okay, so for H1, this one is meant for the steam, okay, 12,000. And then for HS2, this one is meant for the sugar solution, is 3,000. And then you need to calculate for the value of X over K. This one is meant for the stainless steel. Okay, this one is meant for stainless steel because we have three materials involved with this particular question. Okay, so calculate the value of U. The value of U is 2032 joule per meter square second degree Celsius. The area has been given is 1.4 meter square. Alright, and then use the equation Q equals to UA delta T, and you should be able to get your value as 1.577 times by 10 to the power 5 joule per second. Alright, now let's move on to question number 4. Question number 4, this one, a cold room is built within 3 layers. Okay, so this one I have drawn for you. 3 layers, we have wood, plank, and concrete. Okay. The inner layer is made of thick wood. Alright, so this one is the inner layer for the wood. Right, and then middle layer is a 4-inch plank. So remember that the thickness is been given in inch, not centimeter. So what you need to do is you need to convert this particular thickness value into meter rather than you stick it into this British value. And then the outer layer is concrete. So concrete is outer layer. Okay, so the arrow should be from the outside going into the inside of the cold room because the temperature of the cold room is colder compared to the outside temperature. Okay, so for the first thing first, what you need to do is you need to convert this particular value into meter. So it is given in your tutorial whereby 1 inch is equivalent to 2.54 centimeter. So you need to convert from inch to become meter. Alright, so first convert this particular value, then afterwards you need to calculate for the value of overall heat transfer coefficient. So how are you going to do that is by using the equation 1 over U equals to x1 over k1 plus x2 over k2 plus x3 over k3 because we have 3 materials here, wood, plank as well as the concrete. Alright, and this particular equation, remember this one you need to use when it is a flat surface. Okay, for flat surface that does not involve with tubing, of course you are going to use this particular simple equation. Okay, the only equation that you need to use for the ln R0 over Ri, that one will be for the tubing. Okay, so plug in all the values of x1 over k1. It's totally depend to you which material that you want to label as 1, which one you want to label as number 2, material number 2 and material number 3. Alright, and then for overall heat transfer coefficient, after you have calculated, the value will be 0.3593 watt per meter square Kelvin. Okay, remember this particular unit because it has been given to you, the temperature is in Kelvin, and then the of course the energy will be calculated in watt per meter square Kelvin. Okay, and then in terms of the delta T, so delta T, what you need to do is calculate from the higher temperature to the lower temperature. So from T4 to T1, so you should be able to get the value of delta T as 41.7 Kelvin. The area has been given as 1 meter square, and then followed by the final calculation, you need to calculate for the value of Q and use the equation of UA delta T because this one involving with several materials is not a single material. So you should be able to get your final answer as a 14.98 watt. Alright, now let's move on to the following question. Question number 5. Calculate the rate of heat transfer across 2 stainless steel pins. Alright, so we have this stainless steel. A and B is stainless steel pins which separated by 0.4 millimeter air. Alright, so this one is the air and it is being separated at a thickness of 0.4 millimeter. Okay, the thickness of stainless steel pin A is 2.2 millimeter. Okay, and for stainless steel B, for pin B, it is a 1.6 millimeter respectively. So can you see that actually the thickness is different? It is not at the same thickness. The heat transfer coefficient on one side of stainless steel pin of T1 is 28 degrees Celsius, okay, and its heat transfer coefficient is 2.5 watt per meter square Kelvin, whereby heat transfer coefficient on the other surface, whereby the temperature is 21 degrees Celsius, so the heat transfer coefficient is 10.5 watt per meter square Kelvin, okay. Thermal conductivity of stainless steel and air is given as, for the thermal conductivity for the stainless steel is 21 watt per meter Kelvin, whereby for the air is 0.031 watt per meter Kelvin respectively. Okay, so what you need to do is, the first thing, draw the diagram, okay, because this particular diagram is not going to be given to you. So what you need to do is, you need to draw the diagram so that it will ease your calculation. You will have a better a visualization of how to solve your problem. Okay, so first thing first, what you need to do is calculate the temperature difference. Of course, calculate from the higher temperature to lower temperature. Okay, so the temperature difference is 7 degrees Celsius, and then followed by calculation of the overall heat transfer coefficient. So since this one involving with several material, so one surface, okay, surface heat transfer coefficient has been given, okay, and then for one side, and then for the other side you are given with another surface heat transfer coefficient as well, okay. And then the material for the thickness has been given for each material, for each pane, stainless steel pane A as well as stainless steel pane B, and then followed by its thermal conductivity of the stainless steel pane as well as for the air. Okay, for stainless steel, the thermal conductivity is the same value, whether it is having the different thickness, but the material are the same. So that's why for the thermal conductivity of stainless steel, the value is the same. Okay, so calculate the value of U. So this one for the XA, this one I label it for the air. So this one will be easier for me to differentiate between the stainless steel A as well as B, and this one is meant for the air, okay, Ka as well as Xa. So for U equals to 1.9673 watt per meter square Kelvin. Alright, the area is 1 meter square, and then followed by the calculation of Q equals to UA delta T, and the value should be 13.77 watt. Okay, so this will cover for the tutorial chapter 6 number 1. Now let's move on to tutorial 6 for tutorial 6 chapter 6 number 2. Okay, so this one you have another 7 question, but I'm not going to cover for the whole question, because some of the question has been the same question, the same pattern as in your lecture notes. So that one you can refer to your lecture notes. Alright, so now let's move on for question number 1. Okay, calculate the overall heat transfer coefficient. You need to calculate for the U. Okay, so the first task you need to calculate for question number 1 is calculation for the U. Calculate the overall heat transfer coefficient for the tube heat exchanger with inner and outer heat transfer coefficient are 650 watt per meter square Kelvin and 5700 watt per meter square Kelvin respectively. Okay, so it is known that the diameter, thickness and length of the tube are given as in your problem statement respectively. What is the overall? Okay, so the second task, so the first one you need to calculate for overall heat transfer coefficient, then the second one you need to calculate for the rate of heat transfer. What is the overall rate of heat transfer if the inner surface of the tube is 83 degrees Celsius and outer surface of the tube is 25 degrees Celsius, and given the thermal conductivity of the material is 56 watt per meter Kelvin. Okay, so in order for you to solve this particular problem, you need to use this particular equation, because this one is involving with the tubing. For the tubing, we have the diameter, and from the diameter, you need to divide by 2 in order for you to get the radius. Diameter divide by 2, you will get the radius of the tubing. Okay, Remember, I have shown you before, whereby, for example, this one is a tubing, okay, and at the center, this cross section, this one is diameter. However, half of the diameter, this one is radius. Right? And then if let's say you have a tubing that is two tubing, right? So from one tube to another tube, the tubing, it has its own thickness. Okay, so this one is the thickness, the x of the tubing. Okay, so now let's move on to the calculation. So you need to use the equation of 1 over u equals to 1 over h naught plus r naught ln r naught over ri divided by k plus r naught over ri hi. So this particular equation, as much as possible, you need to familiarize with this particular equation. This is to ease and to speed up your calculation, right? Alright, so the value for overall heat transfer coefficient is 520.6 watt per meter square Kelvin. Then you need to calculate for the value of A. Do not assume A as 1 meter square. Okay, no, this one is wrong, because normally this particular area, 1 meter square, is meant for flat surfaces. But for tubing, you need to calculate for the value of A, whereby you need to use the equation of 2 pi RIL. Okay, you need to calculate for the value of Ri, and then the value for A is 0.10053 meter square, followed by the calculation of delta T. Okay, it has been given to you the temperature of the inner surface of the tubing as well as the outer surface of the tubing. This one is the outer surface. This one is the inner surface. Okay, so the temperature difference is 58 degrees Celsius. And last but not least, you need to calculate for the rate of heat transfer equals to UA delta T. Then the value of Q is 3035.5 watt. Alright, so now let's move on to question number 2. The same calculation, the same step that you need to calculate for the value. Cold water flows through a copper pipe with the diameter of 3.4 inch, thickness 0.083 inch. So the same thing goes when you are going to when you are given with the value of inch, the thickness is in inches. Okay, you need to convert to meter. So just now in your previous tutorial, it is known that 1 inch is equivalent to 2.54 centimeter. So what you need to do is you need to convert this particular inch to meter. Okay, so cold water flows through a copper pipe with the diameter and thickness given, cools the air stream that flows outside of the copper pipe. Film heat transfer coefficient for air and cold water are given. Okay, so you need to know which one is the inner, which one of the material is flowing in the inner pipe, which of the material is flowing outside of the pipe. Okay, so I have two tubing. Okay, so from the problem statement, it has given to you that the air stream flows outside. Okay, air stream flows outside of this particular tubing, and then cold water is flowing through the copper pipe. Okay, so this one is cold water flowing inside of this particular pipe, and the outer part, this one is cold air. So the same thing goes, determine the overall heat transfer coefficient. So the first step, you need to calculate for the value of U, alright? And then you need to calculate for the rate of heat transfer. Okay, this one is step number 2. Alright, so for the first equation, the first question, you need to calculate for 1 over U equals to 1 over H naught plus R naught ln Ri, R naught over Ri divided by K plus R naught over Ri Hi. So this particular value of Ri and R naught is important for you to get the right value. So that's why you need to know which material is flowing inside of the tubing, which material is flowing the outside of the tubing. Okay, so the value for U is 42.5093 watt per meter square Kelvin. And then followed by the calculation of the value of area, again using the same equation 2 pi RIL, and the value of the area is 0.0598 meter square. Calculate the value of temperature difference. Temperature difference is 50 degrees Celsius. Alright, this one comes from 70 minus by 20, so you will get 50 degrees Celsius. And last but not least, calculate the rate of heat transfer by using the equation UA delta T. The value is 127.2 watt. Alright, now move on to the following question. Question number 3. Mango juice drink flows through a stainless steel pipe whereby the inside diameter has been given 13.2 centimeter, the thickness is 2.8, that one is the X, and it is heated by hot water which flows on the outside of the pipe. Okay, why the thickness is important for you to know is because you need to plus the value of the thickness plus with the inner radius in order for you to get the value for R0. Okay, R0 is equivalent with Ri plus the thickness of the tubing. Alright. Okay, so it is being heated by hot water which flows on the outside of the pipe. So it is a very clear cut whereby mango juice is flowing in the inside of the diameter, whereby on the outside hot water is flowing. Film heat transfer has been given to you, the thermal conductivity has been given to you, so the same step applies whereby you need to calculate for the overall heat transfer coefficient followed by calculation of rate of heat transfer. Okay, so overall heat transfer coefficient for the pipe, use the equation, the same equation whereby this one involving with the tubing, so 1 over H0 plus R0 ln R0 over Ri divided by K, plus with R0 over Ri Hi, then the value of U, you supposed to get around 532.45 watt per meter square, Kelvin. Okay, and then followed by calculation for the area, because you need to use this particular value of area in order for you to calculate for the rate of heat transfer. So again, using the same equation 2 pi RIL, this one equivalent to 0.4147 meter square. Okay, so delta T, calculate the delta T, the value of delta T is 72 degrees Celsius. Then the final answer for the Q is 15.83 kilowatt. Okay, remember this one I have simplify the value, simplify the answer by convert it to become kilowatt. So it's supposed to be 15.83 times by 10 to the power of 3 watt. So because this 10 to the power of 3, this one equivalent to kilowatt, so that's why I simplify the answer as 15.83 kilowatt. Alright, so now let's move on for question number 4. Question number 4 is the calculation of LMTD. LMTD, this one you can either write down as LMTD or you can also write as delta TLM. It carries the same meaning. Okay, so remember I have explained in the video for chapter 6 of how to simplify this particular equation of LMTD. Okay, so for LMTD, you have two tubing. Okay, one is flowing on the inside and the other one is flowing at the outside. Okay, so it depends whether the movement is flowing co-current or counter-current. So for this particular case, for question number 4, it is a counter-current, okay, counter-flow. So you need to make sure that the temperature is, the arrow going for the material or the correct direction. They are in correct direction. Otherwise, you are going to calculate it wrongly. Alright, so use the equation for LMTD. You need to identify which one is THI, which one is TH0, which one is the temperature for the cold water to goes in, which temperature is for the cold water goes out. Then from there, you are able to use this particular equation. LMTD equals to TH0 minus by TCI minus by THI minus by TC0, because this one involving with the counter current flow. divide by ln Th naught minus by Tci over Thi minus by Tc naught. Okay, so from the values given, the temperatures that has been given in for you in this particular problem statement, so just use the temperature values. Okay, so 20 minus by 10, so you will get negative 15 divided by negative 0.9163. So don't be afraid with this value of negative, because you have learned during your high school year whereby this particular negative and negative, it will become positive. So the value of LMTD is 16.27 degrees Celsius. Alright, so this particular question number 4 has been settled. Now we move on for question number 5. The same calculation, the same step. You are going to calculate for your LMTD, and this particular this particular problem statement for question number 5, the milk is being stirred. Okay, it is being stirred. Alright, so you have this water bath whereby the milk is flowing at a alright, so this is how it's supposed to look like. Okay, so you have a piping that goes around this particular water bath, okay, whereby this is the flows for the milk. Okay, this one is for the milk, and on the inside, this particular cooling water, okay, is being stirred, and it is maintained at 10 degrees Celsius. So for this particular temperature, this particular problem statement, you can use either it is a counter current or co-current, because it will give you the same answer. You can try to use this particular equation of LMTD, whether it is counter current or co-current. At the end, you will get the same answer of LMTD. Okay, because this one, it does not apply for any co-current or counter current. Alright, so the value for LMTD, you can use either co-current or counter current equation, and after that you just plug in all the temperature values given in the problem statement, and the final answer of LMTD you should get as at 19.5692 degrees Celsius. Alright, now let's move on to question number 6. Okay, question number 6, this one what we have I have explained in the video of chapter 6. Okay, the liquid food with specific heat, okay, the CP is 3.5 kilojoule per kilogram degree Celsius, flows in the inner pipe of a double heat exchanger. The liquid food enters the heat exchanger at 25 degrees Celsius and exit at 70 degrees Celsius. So this particular area, this one is meant for liquid food. Okay, this part is meant for the liquid food. Okay, can you see there is a temperature difference given to you? Alright, and then the flow rate of the food is 0.5. Okay, this one is the flow rate, the M. The flow rate, mass flow rate, 0.5 kilogram per second. In the annular section, hot water enters the heat exchanger at 95 degrees Celsius. Okay, given 95 degrees Celsius, and flows counter currently at a flow rate of 1 kilogram per second. The average specific heat of water has been given to you. Assume steady state condition. Calculate the overall heat transfer coefficient if the area of heat surface for this particular exchanger is 47 meters square. Okay, so what you need to do, the first thing first, you need to find for the exit temperature. Okay, exit temperature for the hot water. Alright, so how to do that is by applying the equation of mass balance, mass and energy balance. So use the equation Q equals to mCp delta T. Okay, so one side is meant for the liquid food and the other side is meant for hot water. Okay, remember, because the value for Q will be the same value regardless of whether that one is meant for the liquid food or the hot water, because they are flowing in the tubing that is being separated by the inner tubing and outer tubing. But in the end, there is a heat transfer between these two materials. Okay, so calculate for the exit temperature of hot water, then you should get the value for exit temperature as 76.16. This particular temperature, you are going to use it in order for you to calculate for the LMTD. So the first step is to obtain the exit temperature. Second step is to get the value for LMTD. Okay, and then calculate the value of LMTD by using the equation of counter current, because it has been given to you in the problem statement, whereby the flow of the fluid is flowing